Вот, все говорю. 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 И что, все зря? Да, говорю. И как? Ничего не работает? А, работает? Отлично. Okay, so today we start something completely new, new topic, Frobenius splitting. Sorry. So I will explain shortly what do I mean by this, but what I have in mind is application to the while character formula but then I understand that probably not many of us know this formula. Just who knows this semi-simple Lie algebras, root systems, representations, highest weights? So please raise your hands. Well, I guess you do know. Why don't you raise your hand? And Sergey, you? Well, again, I will formulate it, but the general setting, the semi-simple Lie algebras and root systems, you do know. But you don't. But maybe you can look it up meanwhile. We will develop some general algebraic geometry setup for about a month or maybe 3 weeks. And meanwhile, you can look up the formula itself. So the basic theory, basic structure and representation theory of semi-simple Lie algebras. But the point is that there is semi-simple Lie algebra G, there is corresponding semi-simple group G, and it acts on the flag variety. And the simplest case is when G is SL2 and G is also SL2, and the corresponding flag variety is just P1. So some particular case of this thing you do know. And then you know that all the line bundles here look like O of n, and here they look like O of lambda, where lambda is so-called weight. So I conducted a small survey. So who knows basic structure theory of say simple Lie algebras? Root systems, weights? No? While formula? Do you know?
Yes.
Great. And do you know?
Yes.
Oh, great. So then the majority does know. The point is that if you take the global sections of this line bundle of lambda, and maybe dualize it, then you get certain irreducible module over the Lie group or Lie algebra. And the problem is to compute its character. Character means when you restrict it to the maximal torus inside. And well, there is some answer which was obtained by Hermann Weyl 100 years ago, and there are many proofs, sort of independent, really different proofs. The first one was due to Hermann Weyl and was sort of analytic, but there are some topological and algebraic proofs. The point is that, well, there are two points in the algebraic proof I have in mind. First, you can compute the Euler characteristic of this line bundle. Well, it's also assumed that lambda is positive in some sense. It's called dominant. So if you haven't heard about this, one thing to learn is the notion of dominant weight. And you can compute this, and in fact, this is given by the Weyl character formula. Okay, this can be proved by some Atiyah-Bott-Lefschetz consideration or equivariant Riemann-Roch or whatever. But another problem is that only global sections contribute to this Euler characteristic. All the higher cohomology vanish. Okay. Yeah, right. So there's a general principle that if you have an ample line bundle, then if you take it sufficiently high power, all the higher cohomology vanish. And what is very specific for this situation, for the flag variety, is that you don't have to take any high power at all. It vanishes right away. For any positive line bundle, there is no higher cohomology. Okay, and this is a consequence of Frobenius splitting. Okay, so in fact, I hope we will even prove this. I mean, this implication we will prove already today. And well, that's what Frobenius splitting was discovered for. And then the hard work is to prove that for a flag variety, this Frobenius splitting really does hold. And this will take us like three weeks. Okay, so let me define what I mean by Frobenius splitting. And I will never use any of these for 3 weeks, and then in the end I will just develop some application. So if you haven't heard about this basic structure theory before, you have 3 weeks to learn it by yourself. Okay, so let me formulate some first lemma. And then after I formulate and prove it, I will say what I mean by Frobenius splitting. Well, so first of all, our basic setup is that we have an algebraically closed field K of characteristic P. And so it's finite characteristic. And somehow it'll be very important. Well, whatever we do only makes sense because the characteristic is finite. So then there is this Frobenius automorphism. Well, x goes to x to the power p. And it's really an automorphism. So there is an inverse automorphism. For Arrhenius inverse, x goes to pth root of x. Okay, and now let A be an algebra over this field. And we're interested in its Frobenius sort of morphism. Well, again, A goes to a to the power p. So it's an endomorphism, but it's compatible with multiplication, with addition. So it's an endomorphism of algebra, and its image is called a to the power p. But now it is not an isomorphism, yeah, in general. For example, if your a is just polynomials in one variable, then a to the power p is polynomials in its pth power for this variable. Okay. So now the lemma says that assume that a is a localization of a finitely generated K algebra. Then I claim that A is a finitely generated AP module. We'll say this is the first part. And the second part is that if A is regular, then A is locally free. AP module. And the third part is that, well, I can somehow present explicit basis of this locally free module, but locally. So assume that A is local. And T1 and so on, Tn are generators of the maximal ideal. Then T, the following monomials, T1 to the power I1, so on, Tn to the power In, where all those guys are between 0 and p minus 1, form a basis of A over A to the power p. Okay, so in the local case, I can specify basis explicitly. It's a free module, but for a local ring. But then globally, it means that it's a locally free module. Oh, sorry. It means that smooth spectrum of A is smooth. In the sense we discussed in January, I think.
Sum of AIs equals B here.
No, why? Why?
A
Yes.
power B, then
well, for example, in this case, yeah, it's clear that the basis of this model over that is just 1, t squared, and so on, t to the power p minus 1. And that's an immediate generalization. Okay. So let's prove it. So first, this finite generation. A is evident. Well, in fact, everything here is evident for the polynomial algebra. Right? Now, it means that the finite generation holds for any quotient. It means for any finitely generated algebra, right? Any finitely generated algebra is a quotient of polynomials. And hence, for any localization, just for the following reason, that if we localize our algebra with respect to some multiplicative system, then it's the same as if we take pth power, this multiplicative system, and then localize. But also, if we localize and then take pth powers, it's the same as when we take pth powers of the multiplicative system and then localize a to the power p. Okay, so A is proved, and for well, B follows from C. And we have to prove C. But, well, here I mean that A is regular. Okay. And then just by Nakayama lemma, it suffices to check that those monomials form a basis of the quotient modulo maximal ideal. Well, I don't know, maybe, how should I say? Well, maybe I should say Frobenius of the maximal ideal. So I take pth powers of the elements of the maximal ideal, and well, since the maximal ideal itself is generated by those t's, then this is just a modulo the ideal generated by t1 to the power p, and so on, tn to the power p. Okay, so that's not quite pth power of the maximal ideal, because when I take pth power of the maximal ideal, I can take length p products of any generators, and here I only take pth powers of the generators themselves. Okay, and now there is some nice trick that though this ideal is not pth power of the maximal ideal, still it it is, so to say, commensurable to some power of the maximal ideal. And then we can work in the quotient modular this big power of the maximal ideal, but the quotient modular any power of the maximal ideal for a regular ring, just by definition of smoothness, is the same as for polynomial ring. And for polynomial ring, we already know everything. So that's the general scheme of the argument. The trick is that this ideal contains the maximal ideal to the power Pn, right? Because if I take this high, this long product of any generators, then at least one of them will be in the power P. Okay, so that's true, and it means that the quotient A modular Frobenius of M is the same as the quotient A modular Frobenius of M plus M to the power Pn. And so it contains this, and hence there is a projection from A modular M to the power Pn onto here, right? This is bigger, so there is such projection, right? But this is just the same as if we take polynomial ring in T1, so on Tn, and project it, and take quotient modular the zero maximal ideal to the power Pn. Okay, so, and this is since A is regular. Right? Just by definition of regularity, if you recall, well, not just smoothness. If you recall our studies of smoothness, then it implies that the graded ring, the direct sum of m to the power I, or m to the power I plus 1, is just the polynomial ring. Well, it's isomorphic to this. For a smooth ring, well, in general it's the tangent cone, but for the smooth ring, the tangent cone is just flat space. Okay, so we know this, and then we know that it follows that A modular Frobenius of M plus M to the power Pn is the same as this polynomial ring. Well, let me call it, say, P over Frobenius of M plus M. Well, P more of a bad thing, maybe R. Where R is the polynomial ring. Okay, and for this guy, we already know. Well, it was for n equals 1, but for the same price. So here, t to the power I do generate. Okay, so they do generate, but we have to check that they are linearly independent. And then it's the continuation of the same trick that we can embed A into its completion at this maximal ideal, right? So the inverse limit of A modulo m to the power I, as I goes to infinity. Okay, and again, since m, well, it depends only on these quotients. All these quotients we do know they are the same as for polynomial ring. So in case A is smooth, then this is isomorphic to the ring of power series in T1 and Tn, Taylor power series. Okay, and A embeds into this. So it suffices to prove linear independence over this completed ring. And here it's again evident, just there's no difference from the polynomials. What shall I erase? I don't know. So over A completed those monomials form again a basis of well, over pth power they form the basis of the completion itself, and hence the desired linear independence. Since if we had any relation in the non-completed ring, then certainly it would hold in the completed ring. Okay, so the lemma is proved, but one important thing to take home from this proof is that we can check the smoothness at the level of completions. Yeah, so there is this observation, but also the ring is smooth if and only if, well, so the ring without nilpotence is smooth if and only if its completion is just the ring of power series. Okay? Pardon me?
The completion by definition is this limit.
Yes, absolutely. Mm-hmm.
This is some p-adic completion.
No, it's m-adic completion.
And it means that precisely this. M-adic.
Yeah, just the definition. Mm-hmm. No, Nakayama lemma at this point. In the beginning, yeah, in the beginning we already applied it and erased it. Yeah, so you may forget it. It was that it was for to prove that something is generated by something else. It suffices to know it model maximal ideal. That's it. Okay, so now the lemma is proved, and we can formulate the what I mean by Frobenius. So we can somehow we can globalize this result. So if x is a variety over K, our ground field, then it's locally, looks locally like the spectrum of such algebras. We can consider the Frobenius morphism from X to itself that locally looks just like this. So it is identity on topological spaces. Just raising to p-th power on the level of functions. F goes to f to the power p for local functions. Okay, this is our Frobenius morphism, and then we can consider the push forward of the structure sheaf under this morphism. And then, well, in a sense, it's again the same structure sheaf, but with the other modal structure over itself. So it's again OX, but OX acts on it via f of g equals f to the power p multiplied by g. Okay. So if there is some confusion at this point, maybe it's better to discuss it. Yeah, because then we will always assume this.
Перемоделен другим кольцом.
Well, in a sense, yeah, it's well. So in a sense, I view it as just OX containing OX to the power P. But OX to the power P is isomorphic to OX, so I identify it with OX here. Okay, but then action is written in this form. Yeah. So when I take the push forward with respect to Frobenius, it becomes bigger. Yeah. It contains OX, but we can view it. So yeah, we have OX is contained in the push forward of OX, and then we can identify this with, well, the push forward of anything is just whatever it was, right? The global sections of any push forward. So we have X goes to X by Frobenius goes to the point, and the composition is just the global sections. So if I take this push forward and then global sections, it's just if I took global sections from the very beginning, and then those are just regular functions, right? So in a sense, this is isomorphic to OX. But under this isomorphism, this OX goes to OX to the power P. Okay. This isomorphism is just raising to p-th power. Okay. P-th power. F goes to f to the power p. right? Okay. So now we can give this definition of Frobenius splitting. So the push forward and pull back are adjoint functors, and in particular we have the canonical morphism from OX to the push forward of OX. Well, in this sense, it is just an embedding of pth powers into of pth powers into the whole ring. Yeah, we have such an embedding, this embedding should be split. So X is called Frobenius split. If, well, we are given a Frobenius splitting phi from the push forward back to OX, well, such that the composition phi with this is identity, of OX. Okay. So there is no problem to do this in the polynomial case. I will show it in a moment. But for general varieties, it is somehow very rarely achieved. Say for P1 it holds true, but then for any curve of higher genus, it cannot possibly be true. And in general, it happens only very rarely. But in particular for flag varieties. But it's hard to prove that it holds for flag varieties. For any curve of positive genus, for elliptic curve or any curve, I will explain later on. But just the point is, it's very rarely true. Okay, but certainly this phi must be O linear. Okay, and maybe one more useful notion, that if we have a closed subvariety, yes?
How is the map F sharp defined?
Which map?
F sharp.
This is just from well, if you want, from this diagram, yeah, but from general principles, just because the push forward is adjoint to the pull back, and the pull back of O is again O, so you must have this morphism. I mean, for any morphism from Y to X, you will have such a morphism. Well, just because when you lift functions from the base to the total space, you get functions on the total space. Okay, so if Y is a closed subvariety, with defining ideal IY, then the pair YX is compatibly split if the splitting of X preserves the ideal the defining ideal of y. Okay. And okay. Well, let me give this simplest example with a affine space.
You said that for
Yes.
for A1 is simply
Yeah. So I will. Yeah. So I will do this right away. This splitting phi, in other words, is an well, maybe viewed as an endomorphism, so to say, from OX to OX, such that phi of f to the power p times g is f phi of g. So I say that it is OX to the p linear. Now, it had to be O linear, but now I identify O with O to the power p. Okay, so then I view it as a morphism from OX to OX, but linear only over pth powers. Okay, what is also important that phi of 1 must be 1, because otherwise I could set everything to 0 and it wouldn't be splitting at all. Okay, so that's the most important thing we'll check in what follows. Now there is a remark that if x is proper, then any homomorphism over OX from Frobenius OX to OX, linear over OX, well, any is proportional to a splitting as long as phi of 1 is not 0. Just because on the proper or projective varieties, all the functions are, all the global functions are constants, right? And if you know that the phi does not vanish, then you can dilate it and make sure that phi of 1 is 1. Okay? So in a sense, for proper varieties, there is not much to check, but then it's actually almost never possible to find a non-vanishing phi. Okay, it will be only possible for, example, flag varieties or such or things like this. Okay, but on the other hand, for affine varieties, they are always split, and we will check this. But let's first do the example. So we have the affine space, and Y is the union of all coordinate hyperplanes okay, now we can take pardon me?
Y is disjoint union of
No, why disjoint? No, not disjoint. Like this.
Okay.
So it's not irreducible. It's but connected. Yes. So we set on the level of global functions phi of some monomial t to the power j is by definition t to the power j divided by p. So whatever it means. It means that if j is something, well, what do we have? Say I. No, I is something else. I don't know. What other letters do we have? H maybe. P times H. Then J over P is just H. And it's just zero otherwise. So if it's divisible by P, then we just divide. If it's not divisible, then forget it. Okay. So it's at the level of global sections. And you see that it's linear in this sense. Okay, it's linear over pth powers of functions. And it localizes. So this formula localizes. Namely, we just said that phi of f over g is equal to 1 over g phi of f to the power g, f times g to the power p minus 1. And then it's compatible with this property, so it works like this. So it works at the level of sheaves. Okay, not only at the level of global functions, but at the level of sheaves, because it's compatible with this localization. Fine. So we do have an example of Frobenius splitting, and at some point we will. Maybe I should have erased this. We will see that it's, in a sense, rather general. But first, let's prove that it works for arbitrary affine smooth variety. Yes?
Extend this formula to the localization like this.
Just to be compatible with this property. Somehow given that, there's only one way to extend it, namely this way.
And if g is 1, then...
If g is 1, then just phi of f equals to phi of f. Well, we already know for all regular functions. Right? It is given on monomials and then extended by linearity to all polynomials. And if I want it for rational functions, then it works like this.
And p linearity means
Just this is called OP linearity, yes. That's linear over all pth powers. Okay. So there is proposition number 1. And before we prove lemma number 1, and maybe the example also should be number 1. So it says that if x, y are affine smooth, then they are compatibly Frobenius split. And for the proof, well, we say that X is the spectrum of some algebra, and it contains the ideal A, the defining ideal of Y. And now let's consider the following module. M, it is just the module formed by all, so to say, potentially Frobenius splittings. So they are p-linear morphisms. So phi of f to the power p times g is f phi of g. And inside we have submodule m sub y formed by such p-linear endomorphisms that preserve the ideal. Okay, so we have to find phi in this module such that phi of 1 is 1. Okay. Now M is an A module by the formula F applied to phi acts on G just by F times phi acting on G. Okay. And Mi is a submodule. And then this evaluation at 1 is a homomorphism from these A modules to A itself, right? And we just have to check the surjectivity of this evaluation morphism, all right? Okay, so it is a linear. With respect to this action. And it suffices to check the desired surjectivity after localization and completion at any maximal ideal right? But as we argued at this very corner, after completion, all the smooth regular rings look just the same as the power series rings. And for the power series rings, we already did all the job. Right?
Did you check the L-sharp composition with phi is ID? You didn't check.
No. We.
For AN.
No, it suffices, because of this A-linearity, it suffices to know that phi of 1 is 1. Then automatically phi of any function will be of this.
Phi is a homomorphism, yes?
Yes, homomorphism and alinear. So if you know it for one, then you know it for everything. It suffices just to prove this. Just this surjectivity. And surjectivity is enough to check just fiber-wise, and then I could do it after completion. And after completion, we already know. So it becomes the formal power series ring, and moreover, inside you have this ideal times, and this becomes well, just some T1 and so on, Tm inside here. Okay? So, because we know that Y was smooth, then any smooth affine subvariety in a smooth variety after completion becomes just this. Yeah, it is given by some linear equations, complete intersection linear equations. Okay, and then we just set codimension of Y in X. Phi of sorry, like this is equal to the sum of ai to the power 1 over p times t to the I over p. Just as we did in the polynomial case. Okay, so this is proved, and yes.
About complete intersection. If Y is smooth.
Yes. Then after completion in the formal neighborhood, it is just given by a few independent equations.
After completion of what?
Of the ambient ring.
Okay,
Yeah. Then the ideal is just, well, it just has a few generators, namely the codimension of Y, many generators, and they are independent and they can be chosen as part of coordinates.
they can be chosen linear.
Just because Y is form is smooth. If it is cut out by some higher degree equations, then it cannot be smooth at this point. So after completion, any smooth variety becomes just like a flat space. And the same applies to Y. It also becomes like a flat space. It's one flat space inside some other flat space.
Instance means that m modulo m squared is...
Yeah, but then it implies that all the higher powers modulo the next higher powers are also of the same size. And the completion is just the formal power series ring. Okay. Okay, and now we can prove the desired applications of Frobenius splitting. We will do this right now, and then we will start the hard work of proving the Frobenius splitting for some particular varieties, like flag varieties. Also, for example, the Hilbert scheme of points on a affine plane, or on P2, for example, it is also Frobenius split.
Or is an important notion if some variety is
Frobenius split. Just because it implies higher cohomology vanishing. So I'm planning to explain it right away.
But we have some strong theorems about higher cohomology vanishing by Serre, which we proved.
So Serre just says that if you twist by high enough power of ample bundle, then cohomology vanish. And Frobenius splitting says that you don't have to twist at all. If your bundle is ample, then all the higher cohomology vanish right away. No twisting needed.
But,
It's-
but to see that if variety is Frobenius split, then
Yes.
cohomology vanish, it is a big theory.
No, I will prove it in 5 minutes, if you don't mind.
А это необходимое достаточно условие, если гомологии нулевые, то есть рассчитание.
No. No, Frobenius splitting is a very rare phenomenon. Okay, so the next lemma 2 considers a line bundle or invertible sheaf on X. And then it says that first the Frobenius pullback of L is isomorphic to L to the power P. And second, it says that the Frobenius push forward of the Frobenius pullback of L is just L tensor the Frobenius push forward of the structure sheaf. And this is just a projection formula.
Is L to the power B is tensor power?
Yes. Absolutely.
In all previous discussion, it was tensor.
No. When I write a to the power p, it means the set of all f to the power p for f in
I mean, you wrote OX to the power P lies inside OX. You meant
a.
the tensor is
No. F to the power p is the set of just the same thing. But there is no clash of notation. I think it'll. I hope it's clear what we mean at any particular point.
I said that OX to the direct degree P is.
Well, yeah, I understand that there is also the notion of x like this, and this is a trivial vector bundle of rank p. Yes, but
P, yes.
but this is something absolutely different. Yeah. Okay.
А чем эта формула проекции отличается от того, что мы доказывали в прошлом семестре?
No difference. There is a general projection formula. It applies to one particular Frobenius morphism. It's a particular case of very general projection formula.
Ну, то есть мы здесь ничего доказывать не будем, просто ссылаемся.
Yeah, right. Absolutely, yes. We just refer to the general Frobenius formula. Oh, sorry, general projection formula. And as for the first part, it's also clear, I would say, that, well, say if, say a line bundle L is given by transition functions alpha, what's that, G alpha beta. So we have a covering, yeah, U alpha. Then L to the power P is given by G alpha beta to the power P. So we just apply the Frobenius morphism. right? Or else, if you wish, we can say that just by definition, at the level of invertible sheaves, by definition, the pullback with respect to Frobenius of L is the pullback in the general sheaf theory, but then you tensor over the pullback of OX by OX, okay, and the model structure here is just raising to the pth power. Okay. Okay, so I just, in a sense, I just repeat the same thing. Okay, so well, because of this, it is nothing but the pth power of invertible sheaf L. Okay, so we know this, and it's the key to what we are going to prove, because you see, you want to multiply, you want to twist, or well, given any particular ample line bundle, you know that if you take its sufficiently high power, there will be no higher cohomology, right? But you can take the sufficiently high power, just a power of p, but then each time it will be just taking the pullback by Frobenius. So you just take an iterated pullback by Frobenius. But the pullback by Frobenius, well, to consider its cohomology, you can first take push forward by Frobenius and then take cohomology. But this push forward by Frobenius, if your variety is split, will contain the original sheaf L. Okay? On the other hand, this pullback is already taken to the pth power, or maybe to p squared fiber, or p cubed power. So it will eventually have no higher cohomology. But then any direct summand will have no higher cohomology either. But the original sheaf is a direct summand in the push forward of this. So that's the idea, and let me formulate it and prove it formally. So assume X is Frobenius split. And L line bundle. So then we claim that if some cohomology, well, maybe of L to some high enough power is 0, then already cohomology with coefficients in L itself already vanish. For any I, yeah. Well, for some I. Now, if y in X is compatibly split, then, well, sorry, M. The zeroth cohomology of L to some big power surjects onto the global sections on Y. for some big power of n. Then we have this surjectivity already for the first power. Okay, and let's prove this. So we know that we have a Frobenius splitting. But then, when we just multiply it, the tensor multiply with L, we obtain Frobenius splitting for L. Okay, and hence at the level of cohomology, from the cohomology of L into cohomology of L twisted by the Frobenius of the stature sheaf. Is also split and hence injective. So this is an injection. Okay, the cohomology of L injects into cohomology of this. But cohomology of this is the cohomology, as we know, of its pth power. Okay, so the cohomology of L tensored by the push forward of O is the cohomology of Frobenius push-pull of L, and then we know it's the same as cohomology of X with coefficients in the pullback of L. This is the same as cohomology of X with coefficients L to the power P. Okay, so we conclude that the cohomology of X with coefficients in L is embedded into cohomology of X with coefficients in L to the power P, and then similarly it embeds into cohomology of X with coefficients in L power P squared and so on, and eventually those cohomology vanish, and that's what we wanted to prove. Yeah, so we are given that this cohomology vanish. And we conclude that cohomology of L itself vanish, right?
In a second row, you mean push, not pullback.
Why? I do mean pullback. We are using this.
You use B first,
Well,
and then A.
well, yes. So the Frobenius is a finite morphism, so it has no higher cohomology. Yeah, and so I mean that. Well, any cohomology of X with coefficients in Frobenius of anything at all is just the cohomology of x with coefficients in this. Because we have x goes by Frobenius to x goes just to a point, and it's the same as to go to the point directly. Yeah?
Yes.
Okay.
What question
Yes?
in a third row?
Here,
Yes.
well, we started. So we conclude that this cohomology is the same as cohomology of pth power of L. On the other hand, we deduced here that the cohomology of L embeds into this left-hand side. So it embeds into a cohomology of L to the power p, and to the L power p squared, and so on. Yes.
Why is this map is injective?
Because it's split. Because this is a direct summand of that. Since O is direct summand of this, that just we tensor by L and conclude that L is direct summand of that.
Okay.
And so its cohomology is direct summand of cohomology of that. Push forward. Okay. Okay. Now we have to prove this surjectivity on restriction of y, restriction to y. So we have global sections of L, and we have an embedding into global sections of L to the power p and to the power p squared and so on. And then we have restriction here to the global sections on L, on Y, and then those are also Frobenius splits, so it embeds into global sections of pth power. And well, we can iterate, as you say. Sorry, the power n, big enough power. And we know that this is surjective, but then the compatibly split means that everything here is surjective as well. So once again, these are just direct summands. So since it's surjective on the big space, it must be surjective on the direct summands. Okay. On the ambient spaces implies surjectivity on direct summands. Okay. So let me just formulate what we proved as a theorem, because it's a really great theorem, and then we'll continue next time. So it's a corollary. So assume X is proper or projective over and affine base. And L is an ample line bundle on X. Then first, if X is Frobenius split, then all the higher cohomology with coefficients in L vanish. Yeah, just because of the Serre vanishing. If you take high enough power, they do vanish, but we know that the original cohomology are direct summands of this high enough power cohomology. And second, if Y and X is compatibly split, then at the level of first cohomology, of zero cohomology, global sections, we have a surjection. And all the higher cohomology vanish with coefficients in the ideal of Y twisted by L. They vanish. Well, I have to stop now, and I will stop now, but this is not maybe immediately obvious, but you have to write a long exact sequence of cohomology, and then so first of all, just by what we proved, you have to know this for high powers of L. Then it will follow for L itself. And for high enough powers of L, this will follow if there is no first cohomology of this. And the first cohomology of this, well, it's claimed that they vanish, but they vanish for exactly the same reason. If you twist by sufficiently high power of L, then any higher cohomology, in particular first cohomology, vanish. But because of Frobenius splitting, if it's true for a sufficiently high twist, then it's true for just this twist. Okay. So.
Why do we need that X is proper?
Well, just to have an ample line bundle, so to say. I mean, if it's affine, it's fine right away. Yeah, we already proved, in fact, the Frobenius splitting for a fine case, and any line bundle over a fine variety is ample. Yeah. Okay, so thank you for today. Yes.